We started to look at vertical circular motion last time, and what we did is we looked at two force possibilities. We could have, for example, with the marble going around a loop-the-loop, we had a normal force, and that was what was pushing the ball towards the center of the circle. And that is true for any situation of vertical circular motion where we have surfaces and we have the object on the inside surface. Another example that we looked at was swinging something around on the end of a string, could be a chain, could be a rope, and in that instance we had the tension force was what was pulling the object towards the center of the circle. So there are two possibilities for the forces here. What we also began to do is we started to look at the forces acting on something traveling in a circle, and we had a discussion about the forces at the bottom. First off, at both the top and bottom, they're the locations we're going to be focused on. We'll also briefly talk about the sides of this circular motion example. The sides are not on the course, but it is often useful to have a look at those because it helps complete our understanding of it. So we had the force due to gravity acting, we've just drawn it at the top and bottom, it's also acting at the sides. And we talked about this force F here. And the reason we concluded it needed to be larger than mg is we needed the net force to be pointing towards the center of the circle here. Remember, that could be a normal force if there's a surface or tension if there was a string. Now, when we were swinging it around, we also were talking about the top. And in that instance, we were talking about whether the normal force was going to be the same as or different to mg. Turns out we need a net force towards the center of the circle. mg is already pointing in that direction, so the normal force, or the force of tension, we're just going to call it a generic F, that also needs to be pointing towards the center of the circle. Now we'll notice that that force is not as large as the force at the bottom. In fact, that force is a minimum at that location there. And we have that force varying as this object goes around in a circle. So let's pause for a moment and actually go back to looking at this bottom position, and we'll actually look at the forces that are acting here and write an equation to have to do with them. We want to do some of the forces, and remember I said the direction of acceleration is a good direction to make positive, and because that's towards the center of the circle, we're going to point in that direction. So now, when we do sum of the forces equals mv squared over r, remember we're going to do that because we've got circular motion going on, the forces that we have acting, F will be in the positive direction because it's acting upwards, minus mg is going to equal mv squared over r. So rearranging to solve for that value F, we're going to have F equals mv squared over r plus mg. So a nice expression there to be able to find the magnitude of that force. If we apply the same thing at the top, then we've got sum of the forces again equals mv squared over r. At this position, let's make downwards positive because that's pointing again towards the center of the circle. So that means both F and mg are acting towards the center of the circle, so they're positive. And they're going to equal mv squared over r. So F in this instance is going to be equal to mv squared over r minus mg. So we've got two calculations for the force here. We can see the top one had minus mg, whereas the bottom one had plus mg. So that helps us see that the force is smaller at the top and larger at the bottom. Let's go ahead and make sure we've labeled that just to make it abundantly clear. We're talking about the top here. Here we're talking about the bottom. Really nice. Now, it's not on the course, but I did also want to briefly show you what's going on at the sides. We're still going to have mg acting downwards. Let's try and draw it the same length arrow as we did before. In this instance, the normal force, or the tension force, whatever force it is we've got acting dependent on the situation, is going to be smaller than the one we had at the bottom, but larger than the one we had at the top, so somewhere in between. So I'm going to draw something like that. And it's symmetrical, so let's draw it on both sides. So it's important to remember that vertical circular motion in this kind of context is non-uniform motion. We're going to be traveling at different speeds depending on where we are. And those side regions really show us we have one force that's pushing it towards the center of the circle and one force that's either helping an object slow down or speed up. Now, where are we going to have the object going to be fastest versus slowest? So based on our observations in class, recall that we saw we had the lowest speed that was occurring at the top of its motion, whereas at the bottom of its motion, that's where we had the fastest speed or the highest speed. Now, there's a really important situation that we also have going on here. And we spoke about this in class, particularly when we were swinging the string around on a circle. At the lowest possible speed, that force at the top becomes zero. And we saw that with the string slackening off. It's harder to see when we've got something traveling along on a surface because we can't see the surface's response to see that normal force is zero. But we did notice it if we rolled a ball in the loop-the-loop device and we didn't give it sufficient energy to start off with. It lost contact with the track. So we'll talk more about this next time, but a really important point is at the lowest possible speed at the top of this circle here, that force, F, whether it's tension or a normal force, becomes zero. So we've spoken about the forces. One last thing that I do want to talk about is about the energies associated with the top and the bottom of the motion here. At the top of the motion, what kinds of energy does this object have, I wonder? Well, it's at a height above the ground, so it's going to have gravitational potential energy, and it's not stationary, it's still traveling, so it's going to have kinetic energy. At the bottom, it is no longer at a height above the ground, if we call that the height equals 0 point. So here it's going to have kinetic energy. So it makes sense at the bottom that it had that faster speed that we mentioned, because all of that previous gravitational potential energy has been converted to kinetic energy at the bottom. And vice versa, when we're going to the top from the bottom, that kinetic energy is slowly, partially being converted to gravitational potential energy, but not fully because we still have some kinetic energy at the top. So talking about both forces and energy is the approach that we need to do questions here. Let's actually apply it. So we have a situation here. We have a cart of 1 kilogram mass and it's traveling at 4 meters per second. It's going around a loop-the-loop. I can already see centimeters. Let's get rid of that straight away. In fact, what's also handy to note is for this loop-the-loop, we've just seen the diameter is 0.5 meters. Wouldn't hurt to note for our future selves, the radius is 0.25 meters. Just because I know that's the kind of thing I'd forget, so if I write it down now, just remember when we were talking about the net force equals mv squared over r, we needed that radius. So that 4 meters per second is true along this entire section of track when it's flat, but we're going to start to see a change in that velocity as it starts traveling up this loop-the-loop. We're going to have a minimum velocity at this top position here because that kinetic energy is being converted to gravitational potential energy. We're interested in finding the size of the normal reaction of the track on the 1 kilogram model car when it's at the top of the loop. Really key thing here is to draw a diagram. I'm going to draw just a little one down here. This is our cart. I'm not bothering to draw the little wheels. And we're going to draw the two forces that are acting. So we've got mg, always acting, always good to start off with. And in this case, because we've got a surface, we're going to have some sort of normal force, Fn. Now, for our sign convention, towards the center of the circle will be positive. So that means we're going to have sum of the forces equals mv squared over r. So we're going to have Fn, that's what we're interested in finding in the question, plus mg, because they're both acting towards the center of the circle, so both positive, equals mv squared over r. So Fn is going to be mv squared over r minus mg. Now, we've reached a bit of a standstill here though, because we don't know the velocity of the cart at the top of the track. It can't be this 4 meters per second at the top here, because it must have slowed down as it reached the top of the track. So what that means is we're going to pause on our forces approach and we're going to apply an energy approach. So at the bottom, remember, it had kinetic energy. And at the top, it's going to have some of that kinetic energy will be converted to gravitational potential energy and some remains as kinetic energy. What we know is the total energy at the top of the loop has to equal the total energy of the cart at the bottom of the loop. So all we're going to do is we're going to write an energy expression similar to what we've done in the past. So E total for total energy at top equals E total at bottom. So remember, at the top we had kinetic energy half mv squared. Because we're going to use two different v's, let's use T for top here. And it also had gravitational potential energy, mgh. That's going to equal the energy at the bottom. Here it was just kinetic energy, so half mv, let's use b for the bottom, squared. Now what's really nice here is m appears in every term, so we could cancel that off. You don't have to, but I think it makes life a lot easier. Now I've got halves there, so I'm going to multiply everything by 2 to get rid of the halves. So that means we've got vt squared plus 2gh, because that didn't have a half, and we're multiplying everything by 2, equals vb squared. See how multiplying by that 2 just makes life a little bit easier. Now we're solving for v, t specifically, so we need to start getting that by itself. So vt squared will be vb squared minus 2gh, and we're going to take the square root of both sides. Now you remember, when we've taken square roots in the past, we've always asked positive or negative. Because we're just interested in a speed here, we are going to take the positive. Okay, so the velocity of the cart at the bottom was 4 meters per second, so 4 squared, minus 2 times the value of g, 9.8, times the height. So the height that we need here is the total distance from here to here. So it's that 0.5. Take care with your units. So what's that? So we'd have the square root of 4 squared minus 2 times 9.8 times 0.5. So that would give us about 2.48 ... meters per second. Now, what's actually interesting is the formula that we need on the left here is actually v squared. So if we wanted, we could have actually just found what v squared was. So vt squared is actually that 6.2. So over on the side here, what you could do next when we substitute back in, we would have that mass, 1.0, could have had times that 2.48 ... squared. Now we've got that radius, which is 0.25. And then we would subtract the mass, 1.0 times 9.8. That's one way to do it, and that works perfectly fine. What you could do instead is you could have done 1.0 times 6.2. That was the value of the top velocity squared, on 0.25 minus 1.0 times 9.8. Either of those will get you the same result. Calculating what that result is, we would have 15 newtons for the size of our normal force here. So as a reminder, we started off looking at the forces involved, and that was working fine until we realized we didn't know the velocity of that cart at the top. It couldn't be 4 meters per second because some kinetic energy was being converted to gravitational potential energy. So we used that energy approach to find that missing velocity and put that back into our situation with the forces to be able to calculate that normal force. Now, a very typical next question is coming up here. What is the minimum speed the car must have at the bottom to stay in contact? And let's make that a note. Car must have at the bottom. So it's now saying we're not at that 4 meters per second anymore. We're going to be something less than that, a minimum speed. In order for the car must have at the bottom to stay in contact with the track at the top. So we're going to be looking at a boundary condition here. we've got our loop-the-loop situation again. We've got V of the mass at the bottom, we don't know. And we want to know what velocity must that be in order for this cart to remain in contact at the top here. So what we're going to do is we're going to look at that boundary condition. We're going to let the normal force equal 0 at the top for the very first time. And we're going to look at what velocity would be required for the normal force to be 0 there. Remember, that means that the cart is just not in contact, very similar to when we were swinging things around on the rope and that tension had just gone to 0. This one's a little bit trickier of a concept, so I'm happy to revisit this next lesson. So in that instance, if the normal force is 0, the only force we have acting here is mg, and we'll make that our positive direction. So when we get to writing our force equation, sum of the forces is mv squared over r. And we're talking specifically here, we're talking about the velocity at the top. The only force is mg. So mg is going to equal mv squared over r. So cancelling off these m's, because they appear in every term, we'll have g equals v squared over r. Now, keep in mind, this is talking about the velocity at the top, but we're interested in the velocity at the bottom. Still, knowing information about the velocity at the top is going to help us find out information about the velocity at the bottom if we connect those two together with energy. So let's still write an expression for what v top is. We're going to have multiply r over the other side, it will be gr. So v top will be the square root of gr. That's only in this special circumstance where we're at the minimum speed and we have the normal force equaling 0 for the very first time. So what is that out of interest? That would be 9.8 times the radius of 0.25. So the velocity at the top will be about 1.56 ... not rounding it, just clipping it. Meters per second. So that's going to be useful when we compare the energy at the bottom. Energy at the bottom, we said, had to be all kinetic energy, with the energy at the top. It's going to be GPE plus kinetic energy. So let's write our energy equivalent statement again. The total energy at the top will equal the total energy at the bottom. Doesn't matter which way around you write those. So total energy at the top, we said we'd have half mv top squared plus mgh, and that's going to equal the energy at the bottom is just kinetic energy, so half mv bottom squared. Let's do the trick that we did before, cancel off m's because they appear in every term, multiply everything by 2. V top squared plus 2gh equals vb squared. Now we're interested in finding that bottom velocity, so vb is going to be the square root v top squared plus 2gh. V top squared could have done that trick that we mentioned before. We could have had what's v top squared, it'll be 2.45. See how that avoids us needing to round? So 2.45, or you could have had that previous value and square it, plus 2 times 9.8 times h. Height is still 0.5 meters. Okay, we get a nice 3.5 meters per second here. That seems reasonable because the speed we had before was 4 meters per second with a normal force of 15 newtons, so having a value less than that seems reasonable. Okay, let's look at a few more examples. This one is a bit different. We have a speed bump situation. We've got a 500 kilogram car, perhaps, and we're interested in when the car below will leave the road, and it's talking specifically at the top of the hill here. If we're talking about something leaving the road, we're again talking about that boundary condition where the normal force has just reached 0 for the first time. So normally, we would have mg pointing downwards, and we would have the normal force pointing upwards. Now I know that the normal force would need to be smaller than mg because the net force needs to point towards the centre of the circle. But in this case, they're saying the normal force is equal to 0. So mg is the only thing providing a centripetal force. So in this case, if we're looking at the forces acting, sum of the forces is mv squared over r. Only force is mg again. So cancel off those m's. We're going to have g equals v squared over r. Now when it says when will the car leave the road, what the question is actually meaning is what velocity does that car need to have for that to happen? It's talking specifically the velocity at this point. So we can just work with this equation here. V squared will be gr, so v will be the square root of gr. So v is going to be square root of 9.8 times. Now this curve can be modelled as a circle with radius of 20 metres here. That's the radius. So we've got 20. So that velocity would need to be 14 metres per second. Out of interest, if this were a car, it helps me to put into the context of what would that be in kilometres an hour. So 50.4 kilometres an hour. So if someone was travelling at, say, 55 kilometres an hour, they would actually lose contact with the road and they would continue over this speed bump without actually their cart following along the curvature of the road. So they would actually gain some air, which is not ideal when you are driving. You want your tyres in contact with the road. Okay, another example here. Here we have a skateboarder. The rider begins at rest at the bottom edge, so they're just teetering over the edge and then they're going to be skating down here. We're interested in finding the normal reaction at the bottom. So we've got at the bottom, we'll have mg acting downwards. And I want you to think about whether Fn will be larger than, smaller than, or the same as mg and y. Pause for a moment and think about that. Okay. Hopefully you identified that the normal force needs to be larger than mg in order for there to be a net force towards the centre of the circle here. Okay, so we want to find the normal reaction at the bottom, that's the Fn we've just drawn, and we're told they're beginning at rest at the top edge. Let's write an equation for those forces. Sum of the forces equals mv squared over r. Again, towards the centre of the circle will be positive. So we're going to have Fn is positive because it's acting up, minus mg acting downwards. This step here is the one that's most poorly done, and that sets up the entire question. So always pause and draw a diagram. I still do, and I've seen 100 million, thousands of these. I don't know why I went in that progression. So that would be mv squared over r. So Fn will be mv squared over r plus mg. Yep, we're in that conundrum again. What's v? We don't know. So how are we going to find out? Using energy. At the top, this object has gravitational potential energy, but here it starts at rest, so no kinetic energy. At the bottom, we'll call this the height equals 0 point. So it's going to have kinetic energy, but no gravitational potential energy. So next question is, what's this height? Well, it says the diameter of this is 10 meters. So it means the distance from the center to the bottom here has to be 5 meters. And it's probably better to write 5.0 meters. So energy total at bottom equals energy total at top. At the bottom it just has kinetic energy, half mv squared, and that's good because we're trying to find v, and the total energy at the top, just mgh. Yet again, cancel off the m's. So we're going to have half v squared equals gh, multiply everything by 2, v squared will be 2gh, so v is the square root of 2gh. If you wanted, you could just stop at this point and find an expression for v squared. I'm going to do it the traditional way, but I'd like you to experiment with both. 2 times 9.8 times that height of 5.0. So that's about 9.899 meters per second. So going back here, if we squared that to find v squared, this is 98. So we'd have that mass of the person, it was, I've already forgotten, 60 kilos, times 98, that was the value of v squared. Or again, you could do 9.899 in brackets squared. The radius was 5 meters, and we've got the mass again, 705.6. If I wanted to answer to 2 sig figs, that I could write that as 7.1 times 10 to the 2 newtons. Now, does that seem reasonable? This person is 60 kilos, so if they weren't travelling in a circle and they were stationary at the bottom, their normal force would be approximately 60 times 10. If I use g equals 10, it's just an approximation tool, so 600 newtons. So that looks reasonable. The normal force needed to be larger than mg. About 700 newtons is definitely larger than the 600, so that seems like a reasonable answer to me. Okay, this last question we're going to look at next lesson together because I want to make sure that you have understood these fundamental points that we've spoken about. And we'll also, in a little bit, talk about some shortcuts that we can use for vertical circular motion, particularly these questions that involve loop-the-loop situations. What's really important to remember with these questions, regardless of what kind of situation you're looking at, is A, draw a diagram of the forces, B, write an expression for the net force. Net force will be equal to mv squared over r. And C, if there's any velocities that you don't know, apply an energy approach to be able to find those. And I guess D, there's a fourth piece of information that you need. If you're ever looking at a minimum speed situation, that will be when the normal force or the tension force is equal to 0. So keep all those things in mind, start having a go at the vertical circular motion questions, and we'll go through this final question here together next time.